From my channel listeners, I got a request to review Fuji company board ZK-3002. It is another Fuji company developed TPA3255 board, which drew my attention, and also by the thermal architecture it is capable to run at a full power. So I ordered it. It took 3 weeks until it came, pretty long time, but now it's here and we are reviewing this board. Here are a couple of pictures from promotion, and you can see the product advantages. Digital power amplifier, dedicated inductors, so they have mass-produced inductors, high quality, with high quality capacitors, pretty large heatsink. It has a volume regulator on board that you can set a sensitivity for that particular board. For me, it's hard to comment all those names of electrolytic capacitors. I know only Nichicon. But overall components on the board are great. I would say above average. Here you can see without a heatsink, so heatsink is removed. Here's a chip, and here is a microcontroller which is managing temperature sensor of fan, as well as managing that volume regulation circuits, because here on a board there is one chip. It's electronic volume regulator, and you should provide digital input signal and then it converts to the attenuation. So interesting solution. 3 high quality op amps. I don't know what is this one, but it is under the heatsink, and I was not disassembling this board for a review. It seems decently built. Of course, all possible product parameters. Of course, you are writing everything to the max, but let's be honest, we did the calculations, and this board with 48 volt power supply and 10 amps can give absolutely excellent 250 watts. And 250 watts per channel, it's a tremendous amplifier. Also attractive dimensions. The maximum height is 38 millimeters. You can put in a 1U rack unit, good output connectors, and relatively small dimensions, 120 millimeters in a length and 60 millimeters width. So you can really build a small compact amplifier and use it. One specific thing is this microcontroller, what we have on board. Another one which I'm a little bit cautious about, fan is fed from analog circuits power supply. It's kind of risky. We will check about fan noise. You always should check about the fan noise when it's fed from analog circuits. Yeah, and then high quality operational amplifiers. Now let's look at the board. Here it is, ZK-3002, 300 watt plus 300 watt, and this is what they are capable of at the clipping level. And we can get out 250 watts clean power. It came well packed. It's also packed better than many others. It has a manual. Who cares about the manuals nowadays? Also supplied shielded interconnection cable. Here we have a board, I should say decently built, good components. Those are good connectors, including power connector. All components are good. Electrolytic capacitors are 105 temperature Celsius rated. That's a good sign. And overall components are good. As I said, I'm a little bit worrying about the design of fan. But let's test and then make some, let's say, judgments. Yeah. Now, one thing where I want to draw your attention. Here on the board we have electronic attenuator, what is meant to be managed by a microcontroller. And let's check specs and recommended signals for it. Here is this chip, this M62429P/FP serial data control dual electronic volume controller. So they use non-standard solution, above average, I would say, and it's capable to regulate from no attenuation down to minus 83 decibels. It's for us it's total silence, so it has a broad regulation area with 1 dB step, with low noise, and distortions are below 0.01% if you use it properly. And here is a system block diagram. You have two inputs, and then is electronic volume control and some logical and then data. It's small chip, yeah, only 8 pins, the pin legend. And here is internal block diagram. You have two inputs, and they have this regulation, then buffer amplifiers inside the chipset, and then this generates some reference virtual ground for operational amplifier effective operation. So, and then we have a clock and have data where we receive data from microprocessor. But I want to draw your attention about the total harmonic distortions, very low, up to 0.5 RMS. So by amplitude it's 0.7 volts, but 0.5 volts RMS. And this is pretty low. What happens if we go above those 0.5 volts RMS? No, let's say 3 times more. And those are typical values for modern electronic applications. Even Bluetooth receivers, small Bluetooth receivers providing up to 2 volts output, 2 volts RMS. Then there is a dramatic rise in total harmonic distortions. That means we shouldn't go about 0.5 volts RMS, and this amplifier most probably is built that at 0.5 volts RMS input amplifier is at a clipping level. It would be correct way how to make it. This is one thing what should be considered when you buy this board, that you should operate with a relatively small input signal. It has a high sensitivity. This board has a high sensitivity, and we should take care about it. In some cases we need to attenuate input signal to meet that board requirements. So here is data input format, and there is a code. Each code responds to certain attenuation in the chipset. It's very easy when you write the software in a microcontroller. It's easy to manage. Very good chip. Yeah, and here is more information about it, and you can see that input capacitors recommended minimum input capacitors 2.2 microfarads for lowest frequency audio signal. That means that this attenuator input impedance is about 50 kilo ohms, and with some confidence we can use 10 and 20 kilo ohm potentiometer to regulate volume, and we can put it on input of those circuits, and everything will be fine. Definitely you need put some volume control before that board to really operate in a proper way. We always should be not above this 500 millivolts level, what I mentioned, to be at a low distortion level. This is specific of this board. You should put the volume regulator or attenuator by yourself. And okay, now knowing all those small things, especially about that electronic volume regulator, let's measure board. I will not going to measure total harmonic distortions of this board. I don't care about it. All those boards has a good total harmonic distortion ratings once they're using industrial components. No problems with that. We meet TPA3255 chip parameters, and here I can see there are good film capacitors. Everything is fine, and if we keep input signal no more than 500 millivolts, then everything is fine with that part as well. What measurements I will do? I will measure output filter, how they are tuned. I will look at the whole frequency response, and then probably I will do extra audible measurements about that fan operation. Are there any problems with that or not? And then I will do the live listening and give a summary out of it. Okay, here is our device under the test, and we will do all the tests. I will put camera on oscilloscope and do all manipulations out of that, and just give comments to speed up a process and then show you the critical things. Here we have some small speaker. Also we will test some hum noise and other stuff as a last experiment. Okay, let's do a test. I put 48 volts, and what we see on a 1 kilohertz, nice, great output. And I also set a maximum gain, so you can see that 367 millivolts we are at the clipping level. I will a little bit add more. Yeah, here is already clipping at 30. So we have clean 27 volts out of it, and this is absolutely perfect sine wave what we are getting. So no distortions. And one interesting thing for its third board, and I found out when you wire outputs according legend, what is printed on a board, this is on a reverse. So once the board is in a rigid configurations, you can reverse output polarities with no problems, but by default they are set for the reverse polarity comparing to input signal. Will you be able to hear it? No, you will not be able to hear it. Polarities are reverse. And this is a third board, so I'm really wondering, maybe there is some real reason why to make it in this way, that you have more confidence when working with unipolar power supply, that it is better solution than go in the same polarity as input signal. So from music there is no difference. No one can hear absolute phase. So it will look like a perfect one. Okay, and third thing to test, let's look at a sweep at a lower level. I will reduce input to some, let's say 10 volts output, and let's put a sweep and check the output filter. Here I applied sweep, full bandwidth, and for 8 ohms it's almost flat. A tiny bit of drop, but the filter clearly is optimized for 8 ohm load. And what happens if you put it for 4 ohm load? Yeah, there's a drop. But this is not a bad filter optimization, because in most cases for the high frequencies we have some L-pads for the tweeter, or tweeter itself. It has high at a 20 kilohertz. It's not a 4 ohm tweeter anymore. It's at least 8 ohm or even 16 ohm tweeter in some cases. So this is the right way to optimize it, and you will not hear it. And for 8 ohms you have absolutely flat frequency response. And for no, of course, you have a little bit like accents, but it is 8 ohm optimized board. I would prefer kind of 6 ohm optimized board, but this is a good solution as well, especially if you are using 8 ohm loads. How about 20 hertz gain compared to 1 kilohertz? Okay, let's put frequency of 1 kilohertz. Okay, at 1 kilohertz we have 9.7 volts measured by oscilloscope, and let's put 20 hertz now, and you can see at 20 hertz we are getting the same value as for 1 kilohertz. Going back to 1 kilohertz, here you are. Excellent performance of the board, fantastic. And the last thing, how about okay, square is excellent, absolutely perfect. And how about a ramp? And we will measure ramp on 100 Hertz. Excellent, perfect linearity. And how about at 20 Hertz? Even on 20 Hertz it's almost perfect. So all around this board has very good characteristics, and in my opinion it's perfect. It has a good components, and all basic measurements it's passing without no problems. Okay, one more thing to test, attenuator limits. I will put at highest attenuation and what input signal this board can handle. So I set to the minimum, and what signal we need to achieve a clipping level at 48 volt power supply. And we are really close. In input we have 1.6 volts, and it's clipping at 1.7 volts. Yeah, so we're getting this 27 volts out and clipped. And if we put at a maximum sensitivity, the board maximum sensitivity, 370 millivolts or 0.37 volts, we can do, yeah. It is no minimum 4 times. I would say it is 12 dB regulation. It's significant, yes. So we can use several boards and balance it for a multi-board application. By far not a bad solution, not a bad solution. Okay, and now I'm doing the last experiment. I put a fan at continuous operation with a knob. It's possible to put in a manual operation. I will putting my microphone now close to the speaker, and you can here's a fan noise. At low attenuation state there's a fan noise. It's audible, and it's on the most sensitive hearing area, so you will definitely hear from your speakers, especially if you have higher sensitivity speakers. I'm using very low sensitivity speaker here. That's a problem. So if you put higher sensitivity, the smaller signal what you need in input, now fan noise gone. So, specific problem, and I said it's not the best practice to put a fan on the same power supply line where you have analog circuits. Fan is high consumption and device, and we can count it as a digital element because they are switching between poles, and it's easy to run into problems. And this board has exactly that problem. Also, I'm really surprised that for a high attenuation state it's gaining extra noise. Something is wrong deep in schematics, and this is not good thing. So practically you can use it, or it's recommended to use it in a high sensitivity mode, having maximum gain and minimum attenuation. So in some sense there is no reason to put that a volume regulation or attenuation regulation circuit in a front of all electronics when you have such a problem. When you really put a high level signal in it and or attenuate it, then you get fan noise. That's fan noise, yeah, that's problem. What happens when you disconnect fan? Let's listen. So I disconnected fan. No problem, my voice is far away because microphone is right on a speaker. And now I will connect fan. Problem, disconnected, only noise, connected, fan noise, yeah. So practically this solution I will do it several times. Is it critical? Actually at high attenuation it is critical. And now I do it the same with a low attenuation. That means small signal version. First, noise has gone. and connecting fan, no noise in the speakers. So one thing to really take in account using this board, that normal operation is at a high sensitivity mode, practically inaudible, so fan doesn't have impact. Okay, now my microphone is back, and let's make a summary about this board after we did all those measurements. Everyone is asking how it sounds. It sounds fantastic. It's one of the best boards by sound so far what I reviewed, or which I tested, and mostly because really using good components, starting from capacitors, all industrial grade inductors. Those are important. It has very low distortions, has energy and power, high quality connectors. Everything is fine. A good quality heatsink, also how heatsink is implemented, it's right way how to do that. Acceptable quality fan, excellent dimensions, easy to implement. So many good things. But about the lowlights. Engineers has a great idea to implement that specific chipset with electronic management of input signal level, also regarding those limitations what I mentioned about input level size. Those 1% total harmonic distortions are not a problem, because in a music signal those are only bass. Your vocals are going about 8 times lower level than this maximum input level. So this board is awesome even at a maximum attenuation. So everything is fine here. No complaints about it. With a small signal, no problems at all. But even with a large signal, it's not problems at all. So no complaint there. And overall implementation idea to using this chipset was great. When we are talking about real implementation, then engineers failed. Anything what I will say about a reason why adding attenuation you get more noise, it will be speculation. But my big suspicions are that it's something wrong with this analog circuit power supplies. Because this additional noise what comes when you put a high attenuation, and that everything what you can hear as a fan noise has the same root cause, and it is something with the way how analog circuits power supply has been designed. And I think that there should be one more stabilization cascade for that potentiometer, because this potentiometer is regulating DC voltage supplies to microcontroller. And if there is some problems with that voltage, then you get tons of issues afterwards. At current moment, this board is operating in correct way only on a maximum gain. That means maximum input signal level shouldn't exceed 400 millivolts RMS, and then it's perfect board, no complaints at all. Otherwise, it's great flexibility to regulate input sensitivity is flashed in a closet. I personally can't fix it. It's really tight and small components density on a board. No way to make any additional fixing or find out. Would I recommend this board? Despite of those lowlights, actually I'm recommending this board. You will be surprised how good it sounds. It's very good board, and probably best components what you can find in the market, and the price is unbeatable. I really like this board, and a bit upset that implementation was not at that level as it could be, because engineering ideas are good, but R&D was not done at a necessary level. So my judgment, I recommend this board. Will I use it in my designs? No, I will not. Because I'm choosing only boards what operates at a maximum perfection, and you can find it. See, it's a tough competition in a market, and you can find boards without any issues. But otherwise, I'm rating this board high. Yeah, despite of those lowlights what we had, yeah, there is a way how to implement it and how to use it, and sound quality is awesome.